philanthropist and Microsoft co-founder Paul Allen is going around the world asking experts, what do we need to do to make a breakthrough in climate science? Well, I have the answer for Paul Allen. And the answer is, not from the way that we're doing climate science today. We need a new paradigm. The problem is that climate science today is stuck. We can't predict the future in a way that helps us prepare for it, that gives us the kind of information that's useful to policymakers or municipal planners or to the agricultural sector or other corporate sectors. It's not enough to know that all models agree on what's going to happen in the future, that it's going to get warmer and it's going to get drier. We need to know how. How fast, how severe, what are the tipping points, what are the cost benefits for different solutions? Where do we need to act first and in what ways? We need to know much, much more, and we need to do it almost immediately. But climate science today can't deliver that knowledge because it's paralyzed by three blind spots. First, it's global. It's almost exclusively global instead of local, where people live and where they make decisions. It relies almost solely on models, ignoring a whole rich library of observations from the past that can make us smarter about the future. And it's still siloed in single disciplines when the immense complexities of climate change and its impacts require interdisciplinary approaches. So how do we make this breakthrough in climate science to get us the information that we need for 2050 and beyond? Well, first, let me explain to you why the current climate science paradigm, which is based on how we've been approaching climate science for the last 3 decades, can't give us that information. Here in Los Angeles, what we know is that it's going to get hotter and drier. But in order to plan intelligently for it, we need to know how much worse and in what ways. It's not just warmer and drier, it's also wildfire risk, it's air quality. And it's not just Los Angeles. We need to know what's going to happen in Beijing, what's going to happen in Seattle. And we don't know, and here's why. This shows the range of projections that the current climate science paradigm gives us for changes in Seattle's temperatures in the decades ahead. Now, look at the enormous spread of projections that we have from the very best climate models. Policymakers in Seattle can't make informed decisions about adaptation measures based on this type of spread. And for rainfall, it's even worse. Models disagree on the sign of change for every single season in Seattle. Some models predict more rainfall and some predict less for a given emission scenario. And it's not just Seattle, it's actually just as bad in their forecasts for Los Angeles. Now, what's incredible is that there's actually more uncertainty due to our models than there is due to emissions, whether we stabilize them or whether we fail to cap them at all. Now, that uncertainty is bad enough in the decades ahead at a global level, but when we go to a local level, the model uncertainty gets even worse. And locally is actually where we need to pinpoint accurate and precise information in order to make decisions. So how are we going to make this breakthrough in climate science? My vision, a climate science paradigm that's empirically tested, that's locally accurate, and that's interdisciplinary in scope. And let me tell you why that's the answer. With the old approach, we presume that all climate models are equally valid in their spread of predictions. And we saw how useful that is for planning in a place like Seattle. Now, other climate scientists are realizing the problems with using this model democracy, a democratic approach with climate models, and the need for benchmarking climate models through the use of hindcasts in order to improve their accuracy and to make them that much more relevant on a local scale. So the breakthrough here is we're using all of Earth's history as a rich database of past local climate observations to make us smarter about the future. Here's an example. We went to China in order to assess the accuracy of model predictions. And this is because the Asian monsoon affects nearly 2 billion people annually. Now, the spread of climate model hindcasts is shown in this graph. The spread, as you can see, for the hindcasts is nearly as large as they are for forecasts for the end of the century. Now, our work here at UCLA benchmarking these models shows us that only 2 of them are correct about temperature and water cycle changes here. We were then able to study the physics of these models and figure out why these 2 climate models were correct and why the other ones were not. And then how can we actually then use this knowledge to improve the other ones? So now we know which models we can trust in this region, and we can use this information to better plan for the future. Now, we don't just want to do this for Beijing. We need to do this all over the world. The Mojave, the La Brea tar pits, Mono Lake, these are all of our targets. The Arctic, the Antarctic as well. These types of studies will help us make breakthroughs in our understanding of how climate impacts temperature, rainfall, drought vulnerability, river outflow, glaciers, all at a local level. Now, this breakthrough in climate science can only happen with an interdisciplinary approach. True observational benchmarks and accurate climate model hindcasts and forecasts cannot happen if we're working in silos. Right now, to have a breakthrough, we need 2 things. First, we need interdisciplinary teams with a lot of different skill sets. We need people who are chemists that can read rocks. We need physicists who can think of climate change on the planet as a series of equations. We need ecologists who don't only study organisms and ecosystems, but understand the impacts of environmental change on what they're studying. We need computer scientists who can formulate databases of climate observations, and economists who can extrapolate cost-benefit analyses for adaptation measures. Secondly, we need unique individuals who are microcosms of those teams in and of themselves. We need special people who are highly interdisciplinary to be thought leaders for science and policy in the century ahead. These are going to be the climate problem solvers of the future. Now, my lab here at UCLA embodies this vision. They are advancing this new paradigm for climate science. And here are some of the types of questions that they're working on. Can the Amazon reduce to half of its outflow in a few election cycles? Which climate models are doing the best job at hindcasting temperature and rainfall in Los Angeles? What kind of warming leads to ice sheet collapse? These inquiries are going to yield the kind of vital, detailed information that policymakers need to move forward on adaptation measures in the future. Now, the technology that we've developed in my laboratory for these local observational benchmarks is absolutely remarkable. The scientists who were involved with the landmark Manhattan Project theorized that we might one day be able to make measurements of the kind that I've been pioneering here at UCLA. Already, we've been using it to revolutionize our understanding of Earth's climate history on par with what the Hubble Space Telescope did and with what gene sequencing did for their fields. Our technology also has amazing crossover to other fields, from evolutionary biology to carbon sequestration to medicine. We've been able to cast light on some of the most enduring debates in all of the sciences, not just in climate science, but also, for example, in dinosaur physiology. Now, here's the catch. Right now, I have 12 people working in my lab on this new climate science paradigm. But do you think that 12 people working like this is enough to make the breakthrough we need in climate science? Instead of a dozen people, we need thousands working in this way, who are interdisciplinary, are working locally, and are working empirically. That's my vision. Thousands of scientists addressing climate change with this new paradigm in order to give policymakers exactly what they need. Now, if Einstein was alive today and he was working in climate science, he wouldn't be a traditional climate modeler. The theoretical climate models we've been using over the last few decades does not encapsulate the kind of thinking that we need in order to make a breakthrough now. So let's make that breakthrough in climate science as soon as possible.